introduce our next speaker, Mishra. She's going to talk about work of Malik Younsi about removability, rigidity of circle domains and Koebe's conjecture, of which we heard a lot, right? So welcome, Ridi, and I hope you excuse us for being so late.
It's fine. Can you hear me?
Yes, perfectly.
Thank you. I would like to thank the organizers for giving me this chance. And this paper is by Malik in Advances of Mathematics. Okay. Oh.
Okay.
Yeah. So in this talk, I'm going to talk about these 5 points. So the first one is the big picture. Why we are talking about circle domains, and what is the Koebe's conjecture. And the second one is measurable Riemann mapping theorem, and how this theorem is connected with removability problems. And then the third one is the rigidity. What do I mean by rigidity and when does it fail? And then I will talk about the main results of this paper and how this paper is unique because it contains some new technique. Okay. Oh, sorry. Yeah. So as the first talk, the Armin talked about the circle domains. So the first fundamental question in complex analysis is, can we have some generalization of Riemann mapping theorem? So the Riemann mapping theorem is like, oh, sorry. Oh, no. Yeah. So the Riemann mapping theorem is like any simply connected domain which is not whole complex plane, then that is conformally equivalent to a unit disk. So the next question is, what can we say if the domain has some holes? And this is some circle domain. So a circle domain in Riemann sphere is the domain that has some holes. Holes means that has the boundary component circle or a point. So the meaning is that you exclude circles or a disk from a domain, and it is not required that you are excluding this kind of circle that is finite. You can remove infinitely many circles, and as well as you can remove infinitely many points. In fact, like you can also remove the Cantor set, which is uncountable. So this is circle domain. And then the Koebe in 1918, he proved that any finitely connected domain in Riemann sphere is conformally equivalent to a circle domain. And that this equivalence is unique up to a Mobius transformation. And next, he and Sram, they proved that a domain that has uncountably many boundary components, they are also conformly equivalent to a circle domain. So initially, Koebe proved for finitely connected domain, and then he and Sram, they extended for uncountably many connected domain. And then the Koebe conjecture is the famous one. Like every domain in Riemann sphere is conformally equivalent to a circle domain. So this is still open. And now we start with some preliminaries for to understand the paper. So first, what is the conformal map and what is quasi-conformal map? So a quasi-conformal map in extended complex plane or Riemann sphere is a mapping F, which is defined from between two domains U and V, which is orientation preserving homeomorphism, and that map F satisfies this Beltrami equation. And this equation has been already discussed multiple of times in this talk. So I will be like very quick of regarding this definition. So remember that this mu is called as Beltrami coefficient, and which is a measurable map from U to unit disk, and with this L infinity norm is controlled by this K minus 1 over K plus 1. And a mapping is a conformal if and only if it is a one quasi-conformal. So this is something well known as Wales lemma. So whenever I will say that a map is conformal, this means that I'm talking about one quasi-conformal map. Now, why we are studying this quasi-conformal map? So the one reason that they enjoy a lot of property. The first one is that this set of quasi-conformal mapping has a multiplicative group structure. This means that the inverse of a quasi-conformal mapping is also quasi-conformal. Composition of quasi-conformal maps are also quasi-conformal. And the second one, that it satisfies Lucene property. This means that they map measure zero set to a measure zero set. Now, this is a remarkable generalization of Riemann mapping theorem, which is measurable Riemann mapping theorem. So it says that if U is a domain in a Riemann sphere and mu is a measurable function from U to unit disk D, with the L infinity norm is bounded by 1. So remember that we are excluding L infinity norm equal 1 here. Then there exists a quasi-conformal map on U such that it satisfies this Beltrami equation like almost everywhere on U. And this map is actually unique up to post-composition of a conformal map. So I will emphasize that this post-composition by a conformal map is important because this F composed Z inverse is actually conformal. You are going from a quasi-conformal map to a conformal map, and that is one of the consequence of this measurable Riemann mapping theorem. Now, how this measurable Riemann mapping theorem is related with removability. So what is the definition of removability? So a compact set E in a complex plane. So we are not talking in extended complex plane. We will just take a compact set E in a complex plane, and we will say that set E is conformally removable or quasi-conformally removable if every homeomorphism on extended complex plane. So if every homeomorphism F is defined on C hat, that is conformal or quasi-conformal outside E, is also conformal everywhere. So you take a function f from c hat to c hat. Initially, it was a homeomorphism, and it was conformal in c hat minus e. Then you can show that that function is also conformal in C hat. So this means that you can remove set E in some sense. Okay, so the next one is some example of removable sets. So quasi-circles are removable. Set of sigma finite length are removable. And there are a lot of sets whose Hausdorff dimension is less than 2, and they are also removable. And now there are some sets which are not removable. So if your set has positive area, then they are not removable. This is a result by Wu and Kaufman. So whenever we are talking about removability, we are always considering the set has area 0. And there are some scatter set of dimension 1. They are also not removable. Now, just we have seen the measurable Riemann mapping theorem. It has a very remarkable consequence, and that is that the notion of this quasi-conformal removability and conformal removability, they actually coincide. Like a set, this means that a set is quasi-conformal removable if and only if it is a conformal removable. And that follows from this measurable Riemann mapping theorem. One side is trivial, the another side includes this measurable Riemann mapping theorem in the sense that we have this composition F compose Z inverse, which is conformal, and that is a consequence of this measurable Riemann mapping theorem. Okay. So this is actually what I just said, that this quasi-conformal removability and conformal removability, they actually coincide to each other. Now, if we are talking about removability, then removability has this local property that if E is a compact, then these two are equivalent. So instead of going to whole complex plane, you can deal with a open set that contain your set E. So if you have an open set that contains your set E, then the every homeomorphism from U to FU, which is conformal, then it is also a conformal on holes set U. And here you can see, like, I'm not talking about that your homeomorphism should be globally defined. I am just talking that your homeomorphism should define on an open set that contains the set E. That is enough. So this is called local property. And now the next notion is conformal rigidity. So a circle domain is conformally rigid if every conformal map on this circle domain omega to another circle domain is a restriction of a Mobius transformation. Okay. So some example of a domain which are rigid. So just like Koebe proved that any finitely connected circle domain are rigid. And then by he and Schramm, they proved that if you have a circle domain with countably many boundaries component, they are also rigid. And then they generalize this to a domain which have the sigma finite length boundary. And now we have some domain which are not rigid. And you can see like here, you have this sigma finite length boundary condition. If you break this means that your boundary has infinite length or boundary is too wild to be rigid. So this is a conformal rigidity. And it is believed that if you understand this rigidity concept, then you can be moved closer to proving Koebe conjecture. So in 1994, he and Schramm, they gave rigidity conjecture. And according to that conjecture, for a circle domain omega, E, B, C, these three are equivalent. So if you talk about that your domain is conformally rigid, then you can say that the boundary is conformally removable, or every Cantor set contained in the boundary is conformally removable. So this feels like something very strong, because you are talking about that the boundary is conformally removable if and only if every Cantor set contained in the boundary is conformally removable. So if you prove that every Cantor set in the boundary is conformally removable, you can actually show that the boundary is conformally removable. And that is somehow is very strong. And this also relates rigidity to removability. And we have seen that conformal removability is equivalent to quasi-conformal removability. So this rigidity conjecture is like very strong in some sense. Okay. So this paper of Malik is devoted to study of this conjecture, and he proved that this B and C are equivalent in some certain kind of circle domain. So if your circle domain whose boundary is countable union of circle, Cantor set, and isolated point, then B and C are equivalent. So this rigidity conjecture, he solved for a special kind of circle domain. So he is not talking about a circle domain whose boundary is uncountable union of circle. And he explained that his idea will not work if you try to extend the result to uncountable union of circles domain. Okay, so this is theorem 3. Yes?
You can't have uncountable union of circles.
Sorry?
You can't have uncountable circles.
No, there is an example.
No, because of the separability property, there are only countably many circles in the circle domain.
So he proved that if you can check, like if the points, if these isolated points are accumulation point of infinitely many circles,
yes,
then it is not true that this theorem 3 will, the theorem 3's idea will not work.
Refers to the whole thing, not to piece. Yeah, that's the but the statement person. Yeah, you cannot have an uncountable many circles. This is the, yeah. Okay, thank you.
Oh, so you're not here to talk.
I cannot hear properly. I'm sorry.
If you come closer, it's on. Okay.
You can discuss them just here.
Okay, I'm just at the end of it.
Oh, yeah.
So like, it's like,
Maybe you can discuss this in university,
yeah, that's.
but maybe here, yeah. You can continue, but maybe after
Ah.
talk we can discuss.
Okay. Yeah, and this is the example which I was talking about. And this example is actually by some German mathematician. Yesterday I checked it about the construction, and it's kind of you take this, you take first this circle and you put these small circles in a annulus, and then you, in the second step, you also rescale this circle next, and then you rescale next, and then you take a C hat minus this set, and that is an example that doesn't satisfy the condition in theorem 3, which is countable union of circles.
Is it unbounded?
Yes, C hat minus this set is unbounded. Yes. This is only 3 iteration.
Yeah.
Yeah. Okay, the theorem 3 is, now I'm going to show the proof, and this theorem 3 is a direct consequence of union of certain removable sets are removable. And it was not known earlier that whether union of 2 removable sets are removable or not. So the idea of this proof of theorem 3 is unique in some sense. Okay. And now this is theorem 4. And the theorem 4 is like, sorry. Yeah. Sorry. Theorem 4 is that if you have a complex plane E in the form of this gamma J and the Cantor set CK and the isolated point Z. So where this gamma J is quasi-circle and this CK is Cantor set and this Z or G is a complex number. And then this E is conformally removable if and only if every Cantor set is conformally removable. So this is, we prove first this theorem 4, and then this will give us the proof of theorem 3 as a corollary, because you are talking about the every Cantor set, removability of every Cantor set C. Okay, now the next result is equivalence in rigidity, which is a theorem 5. And the statement is like that a circle domain is conformally rigid if and only if it is quasi-conformally rigid. So the paper consists of 2 main theorems, which is theorem 4 and theorem 5. And in this slide, we will see the proof of theorem 4 and proof of theorem 5. And for them who wants to see the definition of conformal rigidity and definition of quasi-conformal rigidity, again, this is the definition. Okay. Yeah, and the corollary of this theorem 5 is like if you have a domain omega which is conformally rigid and the given function f is quasi-conformal, then your image of your domain omega is also a circle domain, and it also conformally rigid. So omega is conformally rigid, then quasi-conformal image of omega is also conformally rigid. So conformally rigidity is the property that are preserved under quasi-conformal map. And this is a corollary, which is corollary of theorem 5. Okay. Now coming back to theorem 4. And the theorem 4 was the equivalence of B and C of He and Sham conjecture. Like the boundary is conformally removable if and only if every counter set in the boundary is conformally removable. And the idea is highly based on bare category theorem. And so let's see. So the step 1, if E is conformally removable, like E is the union of all these boundary. So union of this circle and these isolated points, CK, and the counter set. So if E is conformally removable, then every counter set is conformally removable. That is by definition. So to prove the converse, we assume that every counter set is conformally removable. And now we want to show that whole E is conformally removable. So we take a function f, which is a homeomorphism and is conformal on complement of E. This means that we want to show that this f is also conformal on whole C hat to show that the E is conformally removable. So now what the trick is that we will use this maximality argument. So we define a D prime, which is the union of all open sets in Riemann sphere for which F is conformal. So of course, to show that F is conformal, including E, we will first show that this D prime is whole sphere. That means that there is nothing in between C hat and D prime. This means that C hat minus D prime is empty. So assume that this is not true, that E hat prime is empty. Then since E prime is countable union of subsets of this circles and the Cantor set, you can write E prime as a countable union of closed set. And then you have this bare category theorem that at least one of them has non-empty interior, has empty interior. And from there you will get an open set that will contains this E. And now you will use the locality property of conformal removability to get the conformal map on U union D prime. And this will contradict the maximality because you were assuming that D prime is the maximum union of all open sets on which your function was conformal. So for me, the proof is highly based on bare category theorem and a clever trick to contradict the maximality argument. Okay, now we move to prove the theorem 5, which is quasi-conformal rigidity if and only if conformal rigidity for a circle domain. Okay, So this proof contains a new technique. So the technique starts from this quasi-conformal deformation of Scotty group. So this Scotty group are denoted by gamma. And for the circle domain, let's assume you have a circle domain omega. And you denote the circle with gamma 1, gamma 2. And now you will generate the Scotty group by reflection Rj with respect to this circle. What do I mean by that? So you define this Rj in a Riemann sphere, which is a reflection along this gamma j. So if your circle domain has 10 circles, then you have 10 Rj. And then you take this identity map and composition of Rj and make the group gamma omega. So gamma omega is a collection of identity map and the composition of this Rj's mapping. And this Scotty group was first defined by Sibner, and where he proved that circle domain is conformally equivalent if and only if it is quasi-conformally equivalent. And then Bonk, Kleiner, and Merenko, they shows the quasi-symmetric rigidity of this Scotty group. So the existence of this group was already in the literature, and people have used it with their convenience. Now, the second notion is the David coefficient. So we say that a measurable function mu from a open set U to unit disk D is a David coefficient if there are some parameter m, alpha, epsilon naught, such that this weak type estimate hold. And this m is in two-dimensional Lebesgue measure because we are in R2. So this David coefficient, as per name, was developed by David. And he tried to study measurable Riemann mapping theorem when this mu was 1. Mu L infinity norm of mu was 1. And there are a strong David coefficient also where you change this weak type estimate by some another parameter. That is a strong David coefficient. And why we need that, I will just explain in a second. So we have this David map. David coefficient. Now we have this David map. So as we say that orientation preserving homeomorphism as a David map, if F is W11 loc, F satisfy Beltrami equation everywhere. And what kind of mu we are taking here? This mu, which was mu was like this David coefficient. So one can see some similarity of Riemann mapping, measurable Riemann mapping theorem, where in measurable Riemann mapping theorem, we were demanding F is in W12 loc, and it satisfies a Beltrami equation where mu was just a measurable function with L infinity norm is less than 1. But now we are talking about some general measurable function mu. And this is called David map. This F is called David map, and mu is called David coefficient of David map F. So as we have seen, there is some resemblance of measurable Riemann mapping theorem. And by measurable Riemann mapping theorem, we get the quasi-conformal map, which satisfies some very beautiful property. So we can expect that this F also satisfies some property. The answer is yes, some property, but it doesn't satisfy a lot of property. And there is a generalization of Riemann mapping theorem, which is David integrability theorem, which was in the literature. Like you can see, this is some, you also get the conformal post-composition by a conformal map where you have a David map G. So you define a David coefficient, and then you define a David map, and then you get David integrability theorem, which mimic measurable Riemann mapping theorem. But why we are doing this? So the whole point of doing all these things was to study when mu, L infinity norm of mu is 1. Okay. Now I will explain some definition which is required to prove theorem 5. And the first one is pullback. So let's be V a open set, mu be a measurable map defined on that open set V, and F is a orientation preserving strongly David map. Then we say that a pullback of mu by F star is this. So this is pullback of mu by F. And why we are defining pullback? Because we are going to talk about some invariant with respect to these stocky groups. So, and this invariance has a very important consequence in circle domain. So we say that the measurable function mu invariant if this pullback of mu is mu. For every function or every group element T in your stocky group. And one thing to notice here that your measurable map, your measurable function is defined on Riemann sphere. And you are talking about invariance of a domain omega, which can be or cannot be whole Riemann sphere. Okay.
Can I ask you to be aware you are late 5 minutes, so maybe about 5 more minutes?
Sorry?
We were late 10 minutes, so maybe you have.
I think I will finish soon, maybe in 5 minutes.
Okay, great. Yeah.
Yeah. Yeah, so the proposition 16, this proposition shows the importance of this David map in circle domain. So what the statement say, like if your F is strongly David map on globally or defined on a whole extended complex plane, and This F is invariant with stocky group gamma. This means that mu of this F star of mu is mu. Then F omega is a circle domain whose stocky group is given by this kind of F gamma F inverse. So here with a help of David map, and you can say that your image is a circle domain. You have given David map, and for some certain stocky group, you shows that is invariant under this David coefficient. And then as a consequence, you will get that the image of that domain F omega is also a circle domain. Okay, and now we are going to prove theorem 5. And the theorem 5, was what? Like quasi-conformal rigidity if and only if conformal rigidity. And for that, we need this lemma 18. And this lemma is a consequence of proposition 19 that has this relation with a strongly David map to a circle domain. So if your omega is a circle domain and it is quasi-conformally rigid, then boundary should have area 0. And the proof of this lemma is technical, and it highly uses this proposition 19 and some another analytic tools from complex analysis. I will skip the proof of lemma 18. And now for the convenience, I have written the lemma 19, which is a result of he and Schramm. And they have shown that if you have a circle domain omega, and this P be a set of its point boundary component, like P be a set of points on the boundary. And let omega prime is omega union this set of boundary points. And let G be a quasi-conformal map which map omega to a circle domain. And mu be a Beltramic coefficient of G, which is restricted to omega prime. And then this mu tilde is invariant extension to C, extended complex plane. Then under this assumption that H is quasi-conformal and this the invariant extension is equal to Beltrami coefficient of H almost everywhere, then you can write G as composition of T and H on omega, where T is a Mobius transformation. So this is like one of the theorem which was proved by he and Schramm, and we use this theorem to show that conformal rigidity and quasi-conformal rigidity, they are same. Okay, now we should go to proof of theorem 5. So now we assume that omega is circle domain, and we want to show that omega is conformally rigid if and only if it is quasi-conformally rigid. So one side, let's say omega is conformally rigid, and we want to show that quasi-conformal rigidity. So we set mu as mu F inverse on omega, and we take the invariant extension mu tilde of mu as because we want to use this he and Schramm result. Now, by measurable Riemann mapping theorem, we have a quasi-conformal map G, which have this Beltrami coefficient almost everywhere same on C hat. Oh no. Then this G of G is conformal, and then you can show the technique, like you can make the Scotty group of omega, and you show that this is invariant under the Scotty group. And that's why by proposition 16, you show that this is a circle domain. And now omega is conformally rigid. We get that this composition of G and F is restriction of a Mobius transformation. And that's why this omega is conformally rigid. So one side uses the measurable Riemann mapping theorem and stocky group invariance. Now for the reverse side, so we say that we assume that omega is quasi-conformally rigid, and we want to show that it is conformally rigid. So now we assume that F is defined from omega to F omega, which is conformal. And now in particular, it's a quasi-conformal by Wells lemma. So it is a restriction of a quasi-conformal mapping of G from the whole sphere by quasi-conformal rigidity. And then by lemma 18, if you have a circle domain and you map by a conformal map, then the boundary has area 0. So now by using T and Schramm, you get this Mobius transformation, and now you write cleverly the map so that it is a restriction of a Mobius transformation. So that's why you get a map F, which is a restriction of a Mobius transformation. This means that this is a conformally rigid. So at the end, what we have proved and what remains. So the result of this paper is we have shown that the equivalence of B and C for large class of domains, conformal rigidity if and only if quasi-conformal rigidity, and rigid domains as quasi-conformal invariant. And this was the first result on the union of removable sets. And now the open questions. Does this A and B hold in general? Is the union of removable sets are still removable? Here I'm talking about any union of removable sets, not only finite union of removable sets. And the third one is can Koebe conjecture be proved for uncountably many boundary components? So till now we were dealing with countably many boundary components, but this idea will not work for uncountably many components. Thank you.
Thank you. Do we have any questions for the speaker?
So
Yes.
I have one of the remarks that for the first
Maybe. Can you hear?
No, can you please come to the speaker so that I can hear?
So hi, Rudy. So
Hello.
I just want to say a remark that the first open question, maybe one direction is given the false answer by Kaira
Kaira, yes.
last year. So
Yes.
now the main thing is that the rigid part is only
Yes.
half direction of the conjecture.
Yeah, I agree.
Yes, I think it's for the A and B, it has the mean set. So Charles actor.
Right, so if you assume your set is counter set.
Yeah, then
Both directions are.
oh yes, I think so. Because
If you don't have any,
control set.
if all the point, if all the boundary components are point components, the conjecture is completely off, both directions.
Yeah.
And it's solved when,
So the counter example has circles.
Yes, has the control part.
Yeah, Kai has a single author paper, correct, Chengxi?
Yeah.
yeah, but you have to come.
Okay, so, no, I'm saying that, every rigid circle domains which have boundary only at the Cantor set, it is removable. I mean, that's true. Yeah, so one side is always like true, that's about the other side. Yeah, so. Yeah. And one more remark, and it's kind of a question itself. Can you please go back to the slide where you mentioned rigidity conjecture? Hello?
Yes.
Oh, yeah.
Rigidity conjecture of what?
I mean, where you mentioned the rigidity conjecture.
Okay. Yes.
Yeah, so just one remark, actually equivalence of A and C is also false by the same example of Kaira Ayala. But my question is, what is the status on the equivalence of B and C? I mean, is there any progress?
B and C are
Yeah,
done by Malik.
No, but it is for the circle domains whose boundary can be written as the countable union of circles,
Yes.
and isolated points. But that is
Yes.
not the case always. So,
Yes.
yeah. I mean, is there any recent progress on the equivalence of B and C?
Honestly, I don't know about this because this is not my research area,
Okay.
and I was interested in learning these things, and this is my first time when I was. Of course, I know the removability, but I don't know the relation with rigidity and removability. I have worked in solo removability setting.
Okay.
But these are something different where you have some quasi-conformal presence. So then the removability is somehow different because then you want to control the distortion also. So I honestly I don't know.
Okay, I
The
just wanted to know
maximum
that.
thing, yeah, the maximum thing I have understood via reading this paper is like he mentioned that his idea is not, it will not be extended for when you have uncountably many circle union.
Okay, because I asked this question because when I was making a slide for my talk, I went to check like how bad a circle domain can get. And online, I found a question by Malik on Math Overflow Net. And there he is asking that whether every circle domain can be written as a countable union of circles, Cantor sets, and isolated points. And that's not. Huh?
The next picture.
No.
this is
That's an
special,
example of.
very special example.
Yeah, that's an example of it. So in that Math
This is
Overflow
correct.
question, there was mention that not every Cantor set can be written like this one.
Oh.
Yeah, and then when I saw in the Riddhi's talk that for these kind of circle domains, B and C are equivalent, so I thought, what about those Cantor sets which cannot be written in terms of like this union of countable union of circles, Cantor sets, and isolated points? Because the point is, countable union of circles is fine, but there, like you can prove using Bayer category theorem that countable union of closed totally disconnected set cannot cover all the point components. So if you take a countable union of closed totally disconnected set, there can still be some non-point components uncountable, which doesn't cover.
Abhishek.
Yeah.
The example which was there, that example is of a circle domain whose
Yes.
boundary is not union of countably many circles.
Countably many circles?
Whose boundary is not the union of countably many circles. So that's what I was saying.
What do you mean by that one?
I think she's saying
That you have a uncountably many circles there.
That is not possible for a circle domain.
That is he has written in page 13.8.
No, I think that's a misinterpretation because a
Um,
circle domain can have only.
He's saying.
Okay.
He's not saying.
Okay.
That the set on the next picture is not a countable union of circles, counter sets, and isolated points.
Yeah, so,
No,
and so the emphasized word is,
wait a minute.
And that's also there.
Yeah.
I mean, that's a bare category theorem point of.